That's one that's just came in. Good morning, Mia. Okay, let's get this show on the road. We're pretty much finished with this section on the integral and test and P series. I want to continue from last time and actually go through from start to finish questions involving, okay, I've already found out that this series converges, right? We've done the integral test, or it's a P series test, whatever it was, I've proved that it converges, but I now want to know what it converges to. And what you do in that case is that you find a partial sum, right? You find S10 or S4 or S57 or whatever you feel like. And that will be an estimate for what the thing adds up to. And what we've got here in front of us, it's a bit messy, but what that does is it says, look, if you want to know the exact value of what this converges to, called S, then you can find S3. But if you do, wouldn't it be nice to know roughly the range that your answer, the real answer, will live, right? And that's what we're going to do today, how to calculate that. So this integral here is called the remainder of n, and this integral here is the remainder of n plus 1. Do you see it's just, you instead of starting at 1, don't you start at 5 or 25, whatever it might be. Now, these questions are very long, so I'm only going to do one to kind of show you. And the guy I'm going to pick is a very straightforward one, because I don't want to make my life any more difficult than it already is that one. Now, can you trust me that that converges? But if you were looking at it, would you agree it's a P series, P equals 4, so it obviously converges, right? Wouldn't take long to prove that. It would take you much more time to prove that it's positive and decreasing than it would to prove that it converges. But we've done that. And so we know it converges. And let's assume that we've already proved that. Great. So now I want to know, what does it add up to? Or at least an estimate of what it adds up to. And you might be asked, or told, whatever it is, to use S5 as an estimate. So the partial sum S5 is 1 over 1 to the 4, plus 1 over 2 to the 4, plus 1 over 3 to the 4, plus 1 over 4 to the 4, plus 1 over 5 to the 4. Are you comfortable with that's the value of S5? Wouldn't that be an estimate to what all of them add up to? But if you look really carefully, isn't that term tiny? Can you imagine 1 over 5 to 4 is going to be really small? So practically speaking, isn't most of the answer already here? Right? Anything else that's going to follow, won't it be really quite tiny? So I expect that this should be a pretty good estimate. So I'll just go to my calculator. Since this one is relatively easy to do, it's going to be 1 plus 1 divided by 2 to the power of 4, plus 1 divided by 3 to the power of 4, plus 1 divided by 4 to the power of 4, and lastly, plus 1 divided by 5 to the power of 4. And the answer that we are getting is 1.080. And I'm doing that to 3 decimal places. Actually, let's add another one. Let's do it to 4 decimal places. So that's what I'm estimating that entire series adds up to. Even although I've only picked the first 5, I'm making the assumption that most of the answer's value comes from the early terms and that the later terms are almost insignificant. So far, so good? Let's do a gut feeling. Do you think that that answer is good to 1 decimal place, 2, 3, 4? How many decimal places do you think that guy and the real answer are going to be similar? put you in the spot you like. Pick a number. How many decimal places do you think it's going to be?
2.
2. Okay. In the middle. So the real answer is probably going to be somewhere around about 1.08, give or take 0.01, right? That kind of thing. Seems good. So how do we find the error? Well, we're going to find this fella, and then I'll use that. So the first one, n is 5. We find the remainder 5. And the remainder 5 is going to be the integral from 5 to infinity of that guy, right? That's what R5 means, right? Starting at 5 to infinity of the same function. And that means we're going to have to go and do a fair amount of work. Just like this. I'm going to call that guy x to the negative 4. Then it's going to turn into add 1 to the power and then divide by the new power. Evaluated from 5 to t. I'll do a little style point in that. Told you this question is going to take forever, but we're getting there. Okay, so it's going to be the limit as t tends to infinity. I'll plug in t, so I get negative 1 over 3t cubed. Take away a negative is basically adding 1 over 3 times 5 cubed. So that's going to be the limit to t tends to infinity. And again, since this is really for notes, I'm putting in as many lines as I think, so I'm not going to skip in. That's ridiculously ugly, but I'll do it anyway. 1 divided by, put a little bracket around it, 3 times 5 to the power of 3, close the bracket, and the answer I get is plus 0.0027, right? Does that match my other accuracy? What's that guy going? Yeah, 4 decimal places. Yeah, that'll work. Now, brute force, negative 1 over 3 times infinity cubed plus a very small decimal. Would you agree that's 0? 1 over infinity. So there's R5. Put a little box around that so I can find it. Now, we also need to find R6. Now, I could start at the beginning and put a 6 there, 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 because isn't that the only difference, right? And here, put a 6, agreed? So if I wanted to save a whole load of trouble, couldn't I just use the fact that I've already done it once? Wouldn't this answer be that guy? Does that make sense? Or, if you wanted to, I'm not going to do it, but couldn't you go through this entire set of working and that's what you would end up with? And now as a decimal, this guy is 1 divided by, put a little bracket around it, 3 times 6 to the power of 3. And the answer we get this time is 0.0015. And this is R6. And the theory says that S, right, what that converges to is going to be somewhere in the range. The guy that we just got, which was what, S4, plus, was it S4? S5? S5 plus R5 and S5 plus S6. And the S guy we got, S5, is 1.0803 plus this number. And it's also 1.0803 plus this number. And so the exact answer, what this adds up to completely, is going to be, let's find out, this number, 1.0803 plus 0.027. 2 zeros there. So 0.0027, which means, 1.083. Interesting. And on the other side, 1.0803 plus 0.0015. And on this side, 1.0818. And I don't know if you're just lucky at guessing or what, Eli, but when you look at that, if you did it to 2 decimal places, aren't they the same? So to 2 decimal places, isn't that my answer? So I know that converges, and I know it converges at least to 2 decimal places is 1.08. Can I get away with 3? Nah. Would you agree that's a 2 and that's a 3? But aren't we darn close to knowing what the exact answer of that is? Now, if I wanted more accuracy, wouldn't I do an S50? Right? In which case that would be an R50, and I put an S there. That should be an R51. Are you comfortable with all the, it's a lot of number crunching here, but are you comfortable with the process of how to estimate what a converging series looks like when you've used the integral test to do it? So the next question is kind of connected to that. How many terms do you need to get S correct to, give me a number bigger than 4. Whole number bigger than 4.
5.
Did you say 5? Okay. No. Let's suppose that I need to know what our guy, you know, the one that looks like this, right? The one we know converges. I'd like to know what it's equal to, right? At least correct to 5 decimal places, right? And the question is, how many terms? Do I need to do 20 terms, right? Do I need to find S20 before I can say that? Or S50 or S2 million, right? What do I need to make that up? Right, that's the puzzle. So what you do is you find R4 and you find out what it needs to be correct to 1, 2, 3, 4, 5 decimal places. Do you notice that I didn't do 0.00001, but I actually did 5 zeros and then a 5. And the reason for that is that when you round something off, isn't it the next digit that decides how you round it off? So can you understand why I put the 5 there? So if I wanted it to be 3 decimal places, don't I want 0.0005? If I wanted 2 decimal places, 0.005. A million decimal places, 0.1,000,000 zeros, and then you stick in a 5, right? So it's a little idiosyncratic. What's that going to do? If you don't do that, if you make this digit here 1, you might say you need 42 when you need 43, right? It's not going to be miles away, you know, but you'll be like 1 short. Sometimes you get the same answer both times, and that's fine, but we want to be precise. So I need to find out not what R4 is directly, I should say Rn, right? Because we don't know how many terms there are. Now, Rn is n to infinity, the function, And I need to solve when is it equal to this horrible guy. And it's going to be a little bit of a, the answer is going to go there. It's going to be a little bit of a number crunching, a little bit not satisfying as far as I'm concerned. So, oh, darn it, we can't have n in two places, can we? Oh, it's a t, good. So it's a limit as t tends to infinity of this fella, which is going to be the limit as t tends to infinity of, yep, add 1 to the power, divide by the new power, evaluated at n and evaluated at t. And that's going to be the limit as t tends to infinity of that guy again. I mean, it's almost identical to the question I did before. The only difference is, wasn't that 5? But now it's called n. So we have the limit as t tends to infinity of -1 over 3 t cubed plus 1 over 3 n cubed. And if you do brute force, you get 1 over 3 times infinity cubed plus 1 over 3n cubed. And so you end up with that guy. So far, so good. This is what Rn is equal to. And we want this to be a very, very small number. So what we are going to end up finishing with is solving a weird equation. And there are tons of different ways to do this. And I'm going to use, as long as you do it to both sides, okay rule. And so I'm going to take that guy and turn him upside down. So that means I need to turn this guy upside down. Are you happy with that? That's not the only way to do it. Couldn't you cross multiply and divide and get to the same place eventually? So far, so good. I'm going to actually find out what that number is. So 1, clear it out. 1 divided by 0.1234, 5 zeros and a 5 gets me to 1, 2, 3, 4, 5. Gets me 200,000. Still with me? Right. What should I do to both sides next? Remember, the goal is to solve for n.
Divide by 3.
Right. Nothing too spectacular. You agree it's just big numbers, but it's still the same math. And so I'm going to take that guy and divide it by 3. And if I do that, I get 66,666.6 repeater, right? Almost there. What do I do to both sides now to find n? Because n is how many terms you need to get the accuracy you ask for. So what do I do now?
Take the cubic root.
Okay. And I've got that I've got that number in here. So can't I just do to the power of 1/3, which is how you get a cube root, third power. And the answer I get is 40.54 and some stuff. And then you have a little hiccup at the end. I do not know if WebAssign is sophisticated to do this little hiccup at the end, but you still need to do it. Doesn't n have to be a whole number, right? Add up first 40 terms, add up the first 52 terms, right? We have to round this guy off then to the nearest whole number. The answer in this case is 41. Would you agree? Here's the little hiccup. Suppose it was 40.2. Just imagine n was 40.2. What would I round it off to in the context of this question?
41.
Correct. Why always up, right? You don't care if it's a 0.2 or a 0.5. You always round up to the next whole number. What's the reasoning behind why you should do that? Any ideas?
Because anything less would not get you the full amount of terms you need.
Yeah, if you rounded down, couldn't you be slightly shy of the answer that you were looking for? Can you imagine? It might only be minimal, but it's enough. So to play safe, shouldn't you always round up? Now, as I said, WebAssign might not be sophisticated enough to do that, right? Because it's a program. Actually, underneath it, it's just a program, right? It just does stuff mechanically. And because it varies the questions, you know, it's not like somebody does one question, writes the answer in. It might say 40. So when you're doing this question in your homework and 40 doesn't work, or 41 doesn't work, but 40 does, right? Well, you just pick one either side of the one you thought it was, and that should get you through it, right? If that's a test or a homework, you know, well, you get 5 guesses, right? You're going to get the right answer, aren't you, eventually? There are only a couple of choices. But if it was a test, for instance, WebAssign might say you're wrong. But when I go back and look at it, I'll know that you're right and I'll fix it. So don't worry about it in the tests. Promised you there was a lot of work in that. It was close to 20 minutes just to do that entire start to finish. There are not an awful lot of homework questions like that, thankfully, but are we comfortable with that process now? And I'm not going to do another one for the pretty obvious reason. I don't want to do all that work again. So hopefully you're good. The last couple of questions, I think the last one, yeah, is just watch a video. So there's nothing there I need to really deal with. And we are finished our section 11.3. Let's move on to 11.4. And 11.4 is called the direct and limit comparison test. So here's my red pen. We keep adding new tests, don't we? What do we know? We know the divergence test, the geometric series test, the p-series test, and the integral test, right? That's where we're right now. I think that's me covered. Now we're going to do the direct test and the limit comparison test. So that's 2 more added to your list. And we're still not finished, right? There's tests to come after this. I think I promised you about 9. I can never remember exactly how many there are. So here is the most important of the 2. And it's the limit comparison test. And I want you to use this test in all situations, except when the series has an unusual term. So let's give you an example of what an unusual term would look like. If you got that guy, if you got that guy, if you got that guy. So if you see a sine, a trig function, an inverse trig function, an e to the 1 over n, an e to the n squared, right? Anything powers, those are unusual. And when these happen, then you should use the direct comparison test. I haven't even told you what the tests are, but I want to get that quite clear. If you try and use the direct comparison test in all the normal situations, because there's a big temptation to do it, half the time you will get the right answer and half the time you will get the wrong answer, right? Half the time you'll say it converges or diverges and you'll be right. But the other half of the time you're going to be wrong because you won't apply it properly. It's not really designed for those situations, okay? So the guy we're going to look at is called the limit comparison test, and he's your go-to guy, unless, you know, weird stuff happens, right? You know, sine squared as well. Anything that doesn't have n's, n cubes, and square roots of n, right? Because that's what this particular test is designed for. Fractions with powers of n or square roots of n in it. That's what the direct and limit comparison tests are essentially to use for. So, still not going to tell you what the limit comparison test is because we have some skill building to do. And this is how to find a similar series, but simple p-series. Oops. That is like the original. And I call this, my made up name, is that we do surgery to it. So we are going to get a series that we're going to be interested in. Does it converge or does it diverge? And we're going to take this series, which tends to be a lot uglier than the normal ones are, right? Messier. And we're going to do some surgery to it and make it into a nice baby p-series, right? So your goal is find out what p-series it is, right? And maybe some geometrics later, right? So let me show you what I'm getting at. Can I be lazy? I'm going to do it once. But can I now just do the sigmas and everybody knows there's a 1 in infinity? Because I'm going to be doing an awful lot of series and you know, as we go through this. So if I was being asked to do that guy, would you agree that guy would be a pretty hard one to do? None of the integral tests work. It's not really a p-series, and the reason it's not truly a p-series right now is it doesn't have a 1 plus n on the top, right? So what does surgery look like? You do a little squiggly Olympic college. That means approximately the same as. That's what it actually means. Pick the biggest power of n on the top. In this case, it's just n. Pick the biggest power on the bottom. In this case, it's n cubed. Do you see that this guy is him? Does that make sense? That this is the simplified version of this guy, right? This is what happens. Surgery, you basically cut big chunks off, right? And leave behind the essence of what that series is. Looking at that series, it is a p-series, right? Because that's our goal. What is the p-value for that series? 2. Right. How about this fella? Right. Would you agree you do not want to have to try and do that one with an integral test? Wouldn't you have a lot of problems trying to integrate that, right? So integral test isn't going to work. Let's see if we can do some surgery to it. What power of n shall I put on the top?
Squared.
Great. What power of n? Well, tell me what to write in the bottom. Let's just phrase it that way. What do I write on the denominator?
N cubed.
Ah, well done. For those who don't see that, it's the square root of n6, which is n squared over n cubed. which means doesn't this guy behave like a 1 over n? And so it's a p series. And in this case, p is 1. But this one. Are we getting comfortable with doing surgery to it? Does it kind of make sense? Okay, what will I call the top and the bottom in this case? What will the top be?
N squared.
Technically, n squared is fine, but I'm going to pick 3n squared. I like to keep the coefficient as well. But n squared works equally correct, and it is okay to do that if you want to. What will the bottom be then?
4n to the 5th.
Would you agree this one simplifies down to 3 over 4n squared? Agreed? Now, if the 3 and the 4 bug you, do what, I think it was Matthew who did it. Wouldn't you just call the top n squared and wouldn't you call the bottom n to the 5 if you don't like numbers? I don't mind numbers, to me, they're quite fine. Would you agree that's a p series? The numbers don't matter. 5 on the top doesn't stop it being a p series, and 2 or 3 n squared on the bottom doesn't stop it being a p series. What is that a p series for? What family is that one in?
Is it p equals 1?
No. 2, yeah. Isn't it n squared in the bottom? N squared means p is 2.
Wouldn't that be n cubed? Because it
Oh,
was n squared
wow,
over to the 5th.
well caught. I didn't do that right. It's cubed. 2 and 5, it's cubed. You're right. So this guy is a p series as well. Any questions about the fact I can't count? But any questions about how to take a series that's basically got powers of n or square roots of n typically, and reduce it to the essence of what it behaves like this?
I have a question.
Yes, Kira.
Is it mathematically wrong to split it up into 2 pieces? Like for the very first one, could you call it
Oh,
the
this
summation
one-
of 1 over n cubed plus n over n cubed?
Yeah, you could do it that way and it would work. But you couldn't do it with these two.
Yeah, okay, gotcha. Thank you.
Right. So in case you were saying, she's saying, well, I know another way to tackle that, and it's quite right. I would just split that as a 1 over n cubed, which is a p series, p equals 3, and then an n over n cubed, which is what, a 1 over n squared, that's also p series, and that one would converge. So right now we've just done a little skill building thing. If I give you a ugly series, can you reduce it into what it behaves like as a p series? We're cool with that so far. Right. And you will need this to do the limit comparison test. So here goes. This is the limit comparison test. First version. If you have sigma an and you have sigma bn, and we know that sigma bn converges, then if the limit as n tends to infinity of an over bn equals a number, and L is any number you like, but it's not allowed to be 0 or infinity. So it can be 2 or 22. Then sigma an converges. So you're going to have a series called AN, and then you're going to create another guy called BN. Do you know who BN is going to be? He's going to be those guys we did surgery to. And if that sigma BN converges, and if the limit of this is a number, as long as it's not 0, then AN converges. And the second one is very similar. If you have two series, sigma AN and sigma BN, but sigma BN diverges, and then if the limit as n tends to infinity of AN over BN equals L, and L is not equal to a number, then sigma AN also diverges. And this test is very often described in a very simple way. Won't sigma AN and BN behave the same, provided the limit of the ratio is a number? So that's how I would say it in English. Sigma AN and sigma BN behave the same, provided that the limit of the ratio is a number. So we already have some guys that we've done before. Remember these guys? So here's my first question. N equals 1 to infinity, 1 plus n over n cubed, right? That is essentially our first guy, right? Now, he is equal to that guy. And so that's essentially my comparison. That's why it's called the comparison test. Don't we compare the original with some other one, right? What do you know about that fella? Well, we've already told you that he's a P series, right? And isn't P equals 2? And doesn't that mean that this one converges? Okay. So far, so good. Now, what a lot of people do wrong here is they stop and they say, ah, this converges, so that one will. But you haven't proved it, because isn't there, you have to show that the ratio is a number. Because couldn't you have screwed that up, especially if it's a really ugly one? And maybe you didn't get the right sigma BN after all. So what we now do is we find the limit as n tends to infinity of AN over BN. And all I want is that this is a number, right? It's equal to 10, a half, 42. I just want a number. If this is equal to 0, you screwed up. That is not the right surgery. You might think it's easy to do, but occasionally you screw up. Didn't I screw up when I did a 3 when I shouldn't have done a 2? Remember? Well, that might be the big difference between it working and it not working, you know, in a different question. So this is going to be messy algebra, because typically both of these are fractions. The first one looks like that, and the second one looks like that. And I put little brackets around them because it helps me see them. Would you agree that is a very ugly fraction to find the limit of? And almost all of these are going to be ugly fraction divided by ugly fraction. So this is the first thing I would do algebraic. Isn't dividing by 1 over n squared the same thing as multiplying by its reciprocal, n squared over 1? Now, would you agree that that's getting to be a little bit nicer? And it's not uncommon, although it doesn't harm every time, that you get a little cancel. Would you agree n squared and n cubed partially cancel? Now, what is the limit of this fraction? You should be able to tell me just by looking, and then we'll tell how we would prove it. I see a finger. Would you agree it's 1? And couldn't I do that by dividing the top and bottom by n? And if I did, my working would look like this. And then I could do brute force. And that would get me 1. How else could I show that that limit was 1? What other method could I use to find the limit of that fraction?
L'Hopital.
Yeah, actually, wouldn't L'Hopital work really quickly? Wouldn't you get 1/1 and get the answer a much faster? Now, I can imagine and I understand that when you're doing homework, you're probably going to cut out a lot of the middlemen because you can see it happening. And that's okay up to a point when you're doing homework. But you got to remember that the answer is not really what we're after here, which is it's going to converge, right? And what we're interested in is, can you prove it in a rigorous mathematical way that the answer is whatever you come to? So I'm much more interested in showing the process. So actually, see if you do the right process, but you screw up the number, you don't typically lose many points from me in the big scheme of things, right? So don't skip that out when you do the midterm, right? It's okay in homework up to a point. Oh, I haven't finished yet. Isn't this a number? Doesn't this converge? So by the limit comparison test, my series, this one, also converges. Cool. It's kind of a nice little package. Okay. Let's try the next one. Next one we did is a lot messier, right? This one. So we have n equals 1 to infinity, n squared over n over this guy. So that's essentially the comparison one ends up being sigma 1 over n. So far, so good. Now, I know what the conclusion is going to be. Isn't this a P series, P equals 1, and that means it's going to diverge? Great. And there is a habit, I can understand it, that when you look at your homework, aren't you probably just going to get 2 dots, converge or diverge, and you're going to hit that one? Bad habit if you don't do practice at the process, because what's going to happen in your test is that you'll forget about all of that test, right? The second part of the test, and you lose at least half, if not more, of your points. So you got to do it. So we are going to find the limit as, n tends to infinity of an over bn. And that's going to be the limit as n tends to infinity of this very ugly fraction over that one. Excuse me. And this guy is going to become n squared plus n over the square root guy times n over 1. And this now is going to become n cubed plus n squared all over that guy. I'll tell you right now, L'Hopital is not a good idea. Would you just agree that L'Hopital and square roots never play well together? Because when you differentiate a square root, don't you get an even uglier answer, not a simpler answer, right? It just gets messier and messier. It goes nowhere. So I really only have one method to solve this.
Isn't it like multiplying by the square root but with a plus or something?
There is a square root and there is a multiply top and bottom to it.
Yeah.
But I would think of it more as n cubed over n cubed. Now, I'm going to adjust that in a second because it's too late now because I've written it. If you divide the top and bottom by n cubed, this guy gets you 1. This guy gets you 1 over n. I don't really do n cubed in this. Shouldn't I call that the square root of n to the 6 so they can play well with this guy, right? So I should have called that guy. That isn't the square of n to the 6 the same thing as n cubed. So what we have inside the square root is a 1, whoops, take away a 1 over n squared. And now I can do brute force on it. And since the limit is a number, right, not 0, but a number, doesn't that mean that these two behave the same? So you finish with, so by the limit comparison test series does that, it diverges. So as long as your fraction has powers of n in it, right? N cubed, n to the half, n squared, square root of n cubes, you know, things that look like that. As long as it's got that, the limit comparison test will work, right? Do the surgery to figure out who he is, prove that the limit is a number, and if you can make this, and I know it's been 1, but it could be 42 the next time, it just needs to be a number, right? Then you can say the limit comparison test, I behave the same way this guy does, and if this guy diverges, then I diverge. It's pretty powerful, but isn't it a niche market? Isn't this only for fractions that have powers in the top and powers in the bottom? Now, what happens if you stick a sine n on the top, right? Or, you know, an e to the n squared, then you'll do that other guy. Remember the one called the direct comparison test that you don't know how to do it yet? But that's the guys that you would use the direct comparison test on. Do you see there's a big difference between these guys, the ones we're doing right now, and the ones where something weird is in there, right? There's something extra that's not an n or an n cubed. So 2 tests for 2 situations. And this one is the first one. I think we're doing good. Any questions?
Do these ones always have to be done on like fractions for polynomials, or can, if it's just like a n cubed?
If it was just an n cubed, I'd use a divergence test. So it's always going to be a fraction.
Okay.
Yeah, somebody said sigma n cubed. Won't you just do the divergence test and the infinite limit would tell you it diverges? That makes sense?
Yeah, that makes sense.
Yeah. Now, you could get a simple fraction that might throw you a little bit. Just off the top of my head. Suppose I wanted to do that one. And that one would qualify as a limit comparison test. What would the surgery get you?
One over n squared.
So you see, it's okay to have 1 in the top, isn't it? I mean, it works. If somebody switched, wouldn't that be a divergence test and it would work? And if they did that, wouldn't it be a divergence test and it still wouldn't work? Right. So, interesting question. I think I've already asked you. No, I haven't. Okay, say your last name and bye-bye. And I will see you tomorrow. I'll hang about for any questions.